This is the second video in our sequence of videos for eigenanalysis using R and use of eigenanalysis in statistics. So we have created a toy data set in the last video. Now we are going to do eigenanalysis on that data set. So we already have seen that data set, so I am not showing the data set to you again. First I have to load Rgl Library Rgl. Let me do that. And because my particular laptop is not able to show OpenGL directly, that's a shortcoming of my laptop, so I have to type this options Rgl etc etc. You do not have to do this if your machine is okay. Now I have to do the very important thing, load that data set into a file, into a variable. That is done by using my data equal to read.table pca.dat and head equal to true. Let's quickly take a look at the data file that I had, pca.dat. You can see that there are various cases. Each case has got 3 values and it ignores the square bracketed things. Now there is a heading column. Heading row. XYZ is a row of headings. When I say head equal to T, or T stands for true, this means the very first row will be interpreted as headings. Okay, so let me just do that, F7, and I get an error message. It says line 101 did not have 4 elements. So it is seeing 4 elements in everything. So let's quickly go down. First of all, there shouldn't be any such problem. Yes, I can see that there is this nonsense line somehow has got into it. So let's get rid of that and then re-execute that line. Yes, and now it is okay. Fine. Whenever you load data, you must make sure that this is what you expected. So type dim my data. It is indeed 100 by 3. If you want, you can also type head my data, which will print by default the first 6 rows of your data set. And you can guess similarly, you can write tail, and that will give you the last things. And indeed I can see minus 0.26 etc, minus 0.26 etc. So this seems that we are in pretty good shape. Okay, now I want to find out the mean of x's, y's and z's. So basically I have the data cloud. I want to find the center of the data cloud. So I have to find the mean of the first column, the second column and the third column, and of course I can do that thing separately by just typing mean, then dat, and the first column of dat. That is the way to specify the first column of dat. You write comma and after that you write just 1, and that is the number. Mean of x, x bar, similarly mean of y and mean of z could be found out. But here is a standard trick in R which says apply my data to mean, which means you apply some function to the matrix my data. Where do you apply it? To means to the columns. So if you write 1, that means the rows. You can write only 1 or 2 in this case. And what is the function that you apply? The function is called mean. So you apply the function mean to each column. So you do not have to write a loop that goes over each of the columns. In one line you get all the values. Let's quickly see what is mn, and you can see the first thing is indeed that thing that we had, minus 0.1255 etc. This is y bar and this is z bar. So in one go I get all the means. The apply is very specific to R. There is often not any analog of apply in other languages, most languages. Okay, then I want to compute the covariance matrix. The covariance, let me just compute it. So this is the covariance matrix, which means this thing 1.5 etc. That is the variance of x, this is the variance of y, and this is the variance of z. Remember that this is after the rotated thing. So when I originally created, I said variance of x should be 1 and variance of y should be 4, but this is the rotated version, so there is no straightforward way of relating that. Now these are the covariances. This is the covariance between x and y. This is the covariance between y and z, and so on. Clearly that is a real symmetric matrix. Now I want to find out its eigenvalues and eigenvectors. For that, the command is this: eigen. The eigen is a built-in function in R. You write eig equal to this, that's just a name of a variable, and also observe that I have put it in an extra pair of parentheses. Now that's a good little trick to know. Suppose, just to illustrate that idea, suppose I have a variable called temp and I write 45. Temp is 45. Now if I want to say that, say some new variable, or I can say temp equal to temp square. Temp equal to temp square, or say temp2 equal to temp square. So it creates that temp2 variable, but it does not show the value. If I want to see its value, then I have to write temp2 by itself. Now in many cases we want to do the assignment and at the same time also want to see it. Then what you do is this: you write that line, but you put it in an extra level of parenthesis, in which case it not only assigns the value but also prints the value. So in one go you can get both the things. So that's what I am going to do now. I will first compute the eigenvalues and then also print them. So I get eigen and you get the eigen decomposition. These are the eigenvalues and these are the vectors. Now 3 eigenvalues, they are always reported in order of decreasing magnitude, and or not order of decreasing magnitude, then in actual order. In this case they are all non-negative, so you will always get the same thing, always get the order is same as order of absolute values. Now the vectors, the first column will be a eigenvector, unit norm eigenvector of the first eigenvalue. The second column will be an eigenvector for the second one and the third one. Now there may be many eigenvectors. If some eigenspace has dimension more than one, there may be many of them. I mean many unit norm eigenvectors. R will produce just some of them. There's no guarantee, except that this matrix vectors is an orthogonal matrix. This is the orthogonal matrix of the spectral decomposition of the covariance matrix. Okay, so I have got these things. So these are the directions, and we know from the standard properties that this first eigenvector gives the direction of maximum spread, the second eigenvector gives the direction of second maximum, third one gives the minimum in this case. So I want to plot these things as lines so that I can see that the directions are really what we intuitively understand from the three-dimensional plot. Now in order to do that, I have to do some preparation because I am going to turn things around. Now when I make the plot, it automatically chooses the range of x-axis, y-axis and z-axis, and if these ranges or the scales used in the three axes are not all the same, then naturally right angles will not remain right angles, so I will not really be able to understand that these directions, these eigenvectors are really perpendicular to each other, that our geometric intuition will not work if the scales are chosen differently. So I must use the same range for x, y and z, and I am trying to find that range out. So R equal to range is a function in R which gives you the pair minimum and maximum. Let me just show you quickly what range does. So if I write a list of numbers, say 1, 6, minus 7 and 45, range will give the minimum minus 7 and the maximum 45. So it is not same as range in statistics, which is maximum minus the minimum. Here range gives you a pair. So and if you give it more than one argument, it will take the union of everything and find the range. For example, if I follow it up with another vector which is 34 and minus 45, in that case, now it will give the minimum as minus 45 here and maximum as plus 45 from there. So you can pass as many list of numbers as you want. It will just give you, take the union of everything and give the smallest and the largest. Now I want my x-axis, y-axis, z-axis range to be large enough such that they can hold these things. They can hold the entire data set together with the 3 lines that I am going to plot. And the lines are all going to emanate from the very center and move. One will move in the direction of the first eigenvector, the next will in the second eigenvector, and the last one will be in the direction of the third eigenvector. And I want each of them to have length, say 10, which is a good thing, so that you can see it visually. If they're all of length 1, then in the plot they are hardly visible. So after some trial and error, I chose that number 10. So what I am doing is this. I am taking my data, that is all the points, then Mn is the center, mean, plus 10 times the eigenvectors. So for all the eigenvectors together, 10 times whatever is the minimum and whatever is the maximum I need to put in order to accommodate everything so that nothing goes out of my plot. So I choose that. So if I look at R, what R is the minimum value minus 8 point whatever and plus 7.15. So if I make all my x-axis, y-axis, z-axis show values from this range to this range, nothing will go out of the plot. Okay, so now I am in a position to make the plot. So I use plot 3D, my data, but now I use x lim equal to r, y lim equal to r, and z lim equal to r. X lim is the parameter which controls the limit of the x-axis, minimum, maximum. Similarly, y lim and z lim. So when I do this, I again get a plot just like before, except that now the points are much tightly clustered with lot of space around them, though that space is going to be used by the lines that I am going to impose. Otherwise, they are just the points that I am already familiar with. Okay, now I am going to add the lines. The first thing that I will do is I will add a segment corresponding to the very first eigenvector. So understand what I am doing. I am adding 2 points. I am joining 2 points, the very center point, mean and mean plus the first eigenvector, so the tip of that. So and one end I have the point mean, which I have called Mn, and the other end I have mean plus, I can call eigenvector evec1. Now mean has 3 components, evec1 has also 3 components. Now the segments 3D, which takes 2 points and joins them, unfortunately will not take 2 points in R3 as its argument. It will take pair for x, start x, end x, then starting y, ending y, starting z, ending z, which is pretty irritating for me, but I have to write them down. So this is what I have done. It is segments 3D. First vector is mean 1, that is x bar plus the corresponding thing, the x component. The second thing, the third thing. So I am starting from the mean and then going towards the first eigenvector. So let's just do this and you will see. So when I do this, you can see that I have got the red line which points in the direction of the first eigenvector, and indeed that is the direction of maximum scatter, as we can see from the interactive plot. Okay, now I do the same thing, but for the second eigenvector I do the same thing, but I will use the green color this time, and I get this plot. So the first one gives you, I have just moved too far. This I have given you the very third eigenvector. I just skipped the second one. I have given you the third one. This is the second one. This is the second one. The blue one is the second one. And you can see that the red one indeed gives you the direction of maximum scatter, blue one gives you the direction of second maximum scatter, and the green one gives you the direction of the minimum scatter. There is hardly any scatter at all along that direction. So this is basically what you do when you perform principal component analysis. So I will spell it out for you. Principal component analysis, which gives you the direction of maximum scatter, next maximum scatter, and so on. And from the eigenvalues that we had computed, so I will do it as $val. You can see the values are 3.15, 1.0, and then this thing is drastically small. And that says that this data set basically resides in a two-dimensional space, even though there are three variables.